All right. Howdy. Welcome back to Chapter 5 lecture. So we are going to continue where we left off from Part 1. This is Part 2 of Chapter 5 lecture. And as you'll recall, we just completed this exercise of example 5.12. And there was something that I wanted to clarify from our lecture on Part 1 that I didn't think was very clear. And we said that the volume for standard temperature and pressure conditions is 22.42 liters. That was one of the things that we had to implicitly use in this solution. You can see it right here. Let me change my ink color. You can see it right here where the 22.42 liters appears as the volume for standard conditions. So I wanted to explain where that comes from and why the volume of an ideal gas at standard temperature and pressure is 22.42 liters. Okay, so we can actually get this directly from the ideal gas equation. So suppose we have 1 mole of ideal gas, and this is at STP, standard temperature and pressure, which, as you'll recall, is 0 degrees Celsius or 273.15 Kelvin and 1 atmosphere of pressure. Okay, so we have 1 mole of this ideal gas. Well, remember that ideal gas means that PV is equal to nRT. This is the equation of state for an ideal gas. And since we're at STP conditions, as was already mentioned, the standard temperature or temperature sub STD, STD meaning standard, is equal to 0 degrees C. That's how we define standard temperature in chemistry, which is, when we do the conversion to Kelvin, 23.15 Kelvin. The standard pressure, P sub STD, is 1 atmosphere. So we can plug these two quantities along with what we know our gas constant is into the ideal gas equation and learn that the standard volume, V sub STD, is equal to nRT sub STD divided by P STD. And of course, as we've already noted, R is equal to 0.08206 liters atmosphere over Kelvin mole. You're going to want to write this R value down on your note card, and it's something that you're going to want to eventually have memorized. It's just much nicer to have these things memorized rather than have to constantly go back and collect them from a note card. Okay, so we can go ahead and plug all of this information, right? We know what N is. We're saying for 1 mole. We know R, we know standard temperature, and we know standard pressure. So we can enter all of these into the ideal gas equation and get that we have 1 mole times our R value, 0.08206 liter atmosphere Kelvin mole, times standard temperature, 273.15 Kelvin. And this is all divided by standard pressure, which is 1 atmosphere. So our moles cancel, Kelvin cancels, atmosphere cancels. And when we plug all of this into our calculator, we'll get that the standard volume is equal to 22.415 liters, which is approximately the 22.42 liters that was used earlier. So standard volume of an ideal gas is 22.42 liters. And so that's where this came from in this example problem earlier, this 22.42 liters. And so you can just keep in the back of your mind, when you see STP, standard temperature and pressure, if you're dealing with 1 mole of ideal gas, that necessarily means that the volume of that ideal gas, that 1 mole of ideal gas, is 22.42 liters. And of course, standard temperature is always 0 degrees C, regardless of how many moles you have, because the temperature of a substance does not depend on the number of moles in that substance. And likewise, the standard pressure is 1 atmosphere. And again, that's independent of the number of moles that you have, because the number of moles is, or the pressure of a substance is independent of the number of moles. Okay, so let's go ahead now and move on to another example. Let's now do example 5.13 in your book. This is a great example because it requires you to start to integrate different concepts that you're learning in chemistry. It requires you to use both gas equation information as well as information from previous chapters. Okay, so let's go ahead and insert this image. And so I go up to here. Oh, I forgot that I can include lines, which is kind of helpful. So I'm going to do that. And I am looking for inserting an image. I might have to do something like this. Yes, I know this is what you really like to watch me do. There we go. Are you having fun? Here we go. Boom. Okay. It wasn't so painful, was it? Except it didn't do it, unless maybe it put it in down here. Nope, it sure didn't. Oh, I bet you it put it in up here. There it is. Okay. Boom. Oop. Boy, it didn't like something. What didn't it like? Let's try it again. Okay, I think it's because okay, that's why. Okay. Well, for some reason it won't let me put it actually into the drawing space, but that's okay. We'll just have to go with it. Where did it go now? Oops. You know what I'm going to do? I'm going to delete this because it's starting to annoy me, and I'm sure you're excessively annoyed yourself, and I'm just going to do it this way. Okay, there we go. I'm done with this. Okay, so we're going to go here. There we go. So we have, in this particular example, a sample of methane gas having a volume of 2.8 liters at 25 degrees Celsius and 1.65 atmospheres. And this is mixed with a sample of oxygen having a volume of 35 liters at 31 degrees C and 1.25 atmospheres. The mixture is then ignited to form carbon dioxide and water, and we're told to calculate the volume of CO2 formed at a pressure of 2.5 atmospheres and a temperature of 125 degrees C. Okay, so the other reason why I like this problem is because this is a combustion problem, right? We have methane, the fuel, plus oxygen, the oxidizer, going to products of combustion, CO2 plus water. So certainly a very important type of a problem since we deal with combustion a lot. All right, so I'm going to take you through the solution technique that I generally follow when I do problems and actually how I teach my students at the university. So the first thing I do is I identify those things that I know, right? So what are the knowns? Well, one known is that we have a volume of methane, CH4, and this is equal to 2.8 liters, right? Remember that CH4 is the same as methane, right? That's the name of methane. And we're also told the temperature of the methane is 25 degrees Celsius, and the pressure of the methane is 1.65 atmospheres. We're also told the volume of oxygen, and this is 35 liters. The temperature of oxygen is 31 degrees Celsius, and the pressure of the oxygen is 1.25 atmospheres. Now, I have to tell you that when I read this, just as a quick aside, I can tell that the people who wrote this problem are neither engineers nor combustion scientists, because you hardly ever would have a situation where your pressure of your fuel and your pressure of your oxygen are different, okay? They would be the same pressure if it's in the same reaction vessel, but whatever, for whatever reason, they wanted to change things up and have you use different numbers, right, in the equation. It's pretty silly, but this is the kind of stuff that you have to put up with. Okay, now there's also a reaction involved, and the reaction is a combustion reaction. So we have methane, CH4, plus oxygen, O2, and this reacts to form products of combustion, CO2, and water, H2O. Okay? And then what we're told is to find the volume of CO2, the pressure, find the volume of CO2 for when the pressure of CO2 equals 2.5 atmospheres and 125 degrees Celsius temperature. Okay. So now let's try to actually solve it, right? And when you look at a problem like this, you have to, before you start to write things down or before you actually start, certainly before you start calculating things, okay, is you want to think through how to solve the problem, okay? So you look at what you're given. So you're given volume, temperature, and pressure of one gas. You're given volume, temperature, and pressure of another gas. You're given a reaction, and then you're told to find the volume of one of the species in the reaction, particularly carbon dioxide, by knowing the pressure and temperature of the species in the reaction, the pressure and temperature of carbon dioxide. So a first question to ask is, can PV equals nRT help us? Okay, so can PV equal nRT help us? And in particular, we can revise this and say that the volume of CO2, that's what we're trying to find, is equal to the number of moles of CO2 times the gas constant times the temperature of CO2 divided by the pressure of CO2, okay? So when we look at this equation, we can see right away that we know R, right? That's just the gas constant. But we also know TCO2 and we know PCO2. So we're almost there, except we don't know this, right? We do not know the number of moles of CO2. Okay? All right, well, let's not abandon using the ideal gas equation just yet, right? And so we can then ask ourselves, how do we find the number of moles of CO2? Well, to answer this, we go back and we look at our reaction. We know that by reacting methane and oxygen will create CO2 and water. And so we can use our reaction. Actually, let me rephrase that a different way and actually ask the question, can we use to find the number of moles of CO2? Okay, so let's take a look. We have CH4. Well, we know how many moles of CH4 we have because we know the volume, temperature, and pressure of CH4. And we can use our ideal gas equation to manipulate this to get the number of moles of CH4. Okay, so we know the number of moles of CH4. Likewise, we know the number of moles of oxygen in our reactants for the same reason. We know volume, temperature, and pressure. And we can use our ideal gas equation to come up with the number of moles of oxygen in the reaction. Well, this methane and this oxygen forms product species CO2 and water. So I know from this reaction, this expression here, how much carbon dioxide I'll make when I mix methane and oxygen together in a combustion reaction, okay? And so by knowing the number of moles of CH4 and the number of moles of O2, we can find the number of moles of CO2. Okay? So that's good. We're making progress. All right, but now there's a caveat, there's a catch. Okay, so there's a caution, and there's actually two cautions. Okay, caution number one: we have to be sure the reaction is balanced. So let's take a look at our current reaction the way that it's written. Okay, we're going to take a look at this right here. So the way that I look at this, I say, okay, I have carbon and methane in my reactants. I have carbon in my carbon dioxide in my products. There's one carbon atom in methane. There's one carbon atom in CO2 for every mole of CO2. So my carbon is balanced between my reactants and my products. Now, if I look at hydrogen, I have 4 moles of hydrogen atom for each mole of methane in my reactants, but I only have 2 moles of hydrogen atom for every 1 mole of water in my products. So my hydrogen is not balanced. Likewise, 2 moles of oxygen in the reactants, 2 plus 1, 3 moles of oxygen in the products. So I need to balance the reaction. So let's go ahead and balance the reaction. So I rewrite the reaction in its unbalanced form, CH4 plus O2, and you'll notice that I'm leaving spaces here, okay? I'm leaving spaces there because I'm going to write molar coefficients in front of these terms as I balance the reaction. So how do I balance this reaction? Well, the first thing I do is I assume 1 mole of methane. And I can do that because if I make this 2 moles, that's simply going to double all the coefficients in the reaction. Or if I make it half a mole, it's simply going to half each of the coefficients in the balanced reaction. So the number of moles of methane that I have participating in this reaction is arbitrary. I can make it whatever I want, just so long as I consistently balance all the other species in the reaction. And I, just out of simplicity, assume 1 mole, right? It's easier to deal with the number 1 than it is with a multiplier of some form. The second thing I do is I balance carbon. I balance the first species in my first molecule. And so what I'm going to do after balancing carbon is I'm going to balance hydrogen. And once I balance hydrogen, that means that the balance of carbon between reactants and products will be fixed, and the balance of hydrogen between reactants and products will be fixed. So I can then use the number of oxygen atoms that exist in the products to then balance the amount of oxygen in the reactants, okay? And so I balance carbon in products. I balance hydrogen in products. And then I go back and I balance oxygen in reactants. Okay? And so I do this by setting up a little table. So I have R reactants and P for products. And we have C, H, and O. Okay? Carbon, hydrogen, and oxygen. So in the reactants, when I have 1 mole of methane, I have 1 mole of carbon in the reactants. And then because I have 1 mole of carbon atom per mole of carbon dioxide molecule, that means that I'm going to have 1 mole of CO2 in my products. So my molar coefficient in my products is equal to 1. Real quick, if this had been ethane instead of methane, right? So if it had been C2H6, that's ethane, then the number of moles in my products would be 2 CO2 because I have 2 moles of carbon atom in my fuel, and I need to then have 2 moles of carbon atom in my products. Okay? Okay, now I have 4 moles of hydrogen atom in my reactants, and I have 2 moles of hydrogen atom per water molecule in my products, and so I need 2 times 2 moles of water. Let me rewrite it this way. I need 2 moles of H2O to give me 4 moles of hydrogen atom in my products. And so my molar coefficient in front of water will be 2. 2 times 2 is 4. That balances the 4 hydrogen atoms in the reactants. Now I know that I have 2 moles of oxygen atom from the CO2 plus 2 moles of oxygen atom from the water. So this is 1 times 2 plus 2 times 1 equals 4 moles of oxygen atom in my products. And then I consequently need 2 moles of oxygen molecule in my reactants. And so my molar coefficient in front of the oxygen molecule is also equal to 2. All right, now this, therefore, is a balanced reaction. And this was important because this now allows me to say that for every mole of methane, reacted with oxygen gives 2 moles of CO2. Oh, excuse me, gives 1 mole of CO2. I'm so sorry. Okay, so it's 1 for 1. Okay, now, so I know that based on the number of moles of methane I have in my reaction, I can have some indication of how much CO2 I have in my products. But now this is where caution number 2 comes, okay? So caution number 2 is I have to be sure of which reactant species limits the reaction. Okay? So theoretically, I can concoct a situation where I have exactly 1 mole of methane and exactly 1 mole of oxygen to give exactly 1 mole of CO2, or excuse me, I can have a situation where I have 1 mole of methane plus 2 moles of oxygen to give exactly 1 mole of CO2 and 2 moles of water. But in real life, I'm not going to have those exact ratios of 1 mole of methane and 2 moles of oxygen. I'm going to have either more methane than what I have oxygen available to react with, or I'm going to have less methane than what I have oxygen available to react with. And whichever species is less is the species that's going to limit the amount of products I make. And we call that species the limiting reactant, the reactant that runs out and causes the reaction to stop proceeding, okay? So in order to determine what the limiting reaction is, I now need to calculate the number of moles of methane based on this information and the number of moles of oxygen. And so I can say that the number of moles, NCH4, of methane is equal to the pressure of methane times the volume of methane divided by the gas constant times the temperature of methane. Okay? So, when I plug all of this in to the various known parameters that I have, we get that the number of moles of methane is the pressure of methane, which is 1.65 atmospheres, times the volume of methane, 2.8 liters, divided by the R value, which is our good friend 0.08206 liter atmosphere per Kelvin mole, times the temperature, which is 298 Kelvin, okay? And as a reminder, this pressure, volume, and temperature was given to us in the problem statement. That was known information. Okay, so I plug this into the calculator and I get that the number of moles of methane is equal to 0.189 mole. Likewise, I can calculate the number of moles of oxygen. So this is the pressure of oxygen times the volume of oxygen divided by R times the temperature of oxygen. So again, using the known pieces of information we were given in the problem statement, the pressure of oxygen is 1.25 atmospheres. The volume of oxygen is 35 liters, divided by our good friend R, and times the temperature, which is 304 Kelvin. We plug all of this into a calculator and we get that the number of moles of oxygen is 1.75 moles. Okay, so now we know the number of moles of methane that's available to us in the reaction. We know the number of moles of oxygen that's available to us in the reaction, okay? And we note that for every 1 mole of methane, we use 2 moles of oxygen. We got that from our balanced reaction. Okay, we got that from this expression up here. And so we have NCH4 in our actual reaction of 0.189 moles. That means we need 2 times the number of moles of oxygen to burn the available methane. So that means that the number of moles of oxygen that we need is 2 times 0.189 mole, which is approximately 0.38 moles. But, of course, we have, so the number of moles of oxygen that we have is 1.75 moles. So we have plenty of oxygen. This would be what we call a fuel-lean combustion reaction. So we have plenty of oxygen. And the limiting reactant is thus methane. Okay, so now that means that the number of moles of carbon dioxide that we actually make, okay, is equal to the number of moles of methane that we have, and so this is equal to 0.189 moles. Now we can finally get to the point and say that the volume of CO2 that is produced in this combustion reaction is the number of moles of CO2 times the gas constant times the temperature of CO2, all divided by the pressure of CO2. And so this then becomes 0.189 times our good friend 0.08206 times the temperature of 398.15. Don't forget to do the conversion. And this is all divided by pressure of 2.5 atmospheres. And so we plug this in and get a CO2 volume of 2.47 liters. And that is our corresponding response to that question. Okay, so that completes section 5.3 for us. And so to start section 5.4, I'm going to actually go to a new note here because this is starting to get a little buggy for me. And so we can go ahead and move on to section 5.4, which is what we call the molar mass of a gas. And so how we define the molar mass or capital M that's defined as follows. The molar mass of a gas is its mass divided by the number of moles in that mass, which is just M divided by N, number of mass divided by number of moles. Okay, now we can integrate this into the ideal gas equation where we say that PV equals nRT, and we can substitute an expression for N, we can rewrite our definition of the molar mass and say that N is equal to M divided by big M, little m divided by big M. And so we can write then as, substituting this expression in for number of moles N, we get that PV equals little m divided by big M times RT all divided by V. And so we just algebraically rewrite this as MRT divided by big M times V. Okay, now this is nice because we can recall that density of a substance, any substance, not just a gas, this is how density is defined. And I use the Greek letter rho, looks like a little squirrely p, but this is the Greek letter rho, to define density. And so rho is equal to mass divided by volume. And so I can substitute that into my expression, my ideal gas equation, and get that the pressure of an ideal gas is equal to the density rho times the gas constant times the temperature divided by the substance's molar mass. Okay, so as before, P is pressure, rho is density, and this is often density written as grams per liter. You have to be careful on units. R is the gas constant, 0.08206 liter atmosphere Kelvin mole. T is temperature in Kelvin. And molar mass M is usually grams per mole. Okay? But you have to be careful about these units. And that's why I am such a stickler for units. You really have to keep track of them because sometimes these parameters change or you're given values with different units and then you have to make adjustments accordingly. Okay? But this is a nice form of the ideal gas equation written in terms of density and molar mass as opposed to written in terms of number of moles. Okay, so now let's go ahead and move on to another new section. And so this is now section 5.5, which is Dalton's law of partial pressures. Okay, so up to this point, we've only concerned ourselves with a single species of a gas we also need to understand how to work with mixtures of ideal gases. Okay? So let's suppose we have a volume, and this volume contains a mixture of gases. A mixture of different gases behaving as ideal gases. Okay? So perhaps we have the species circle in this volume. Perhaps we have the species triangle, right? We don't actually have triangle species or circle species. I'm using circles and triangles to represent different species or different types of gases that are in a mixture. And we might also have species dot as a gas in this mixture. Okay? So this particular gas has 3 different species in it: circular gases, triangular gases, and dot gases. Okay? All right, now, of course, these gases are contained in a volume, right? Based on the size of this container here. They are also at a temperature. And as a mixture, they are at a pressure that is this entire volume, okay? These gases are in totality exhibiting a pressure on this volume that is the composition of all the individual pressures that each individual species is exerting on the volume, okay? And what that means, if I say that a little bit differently, is that each species in this mixture is exhibiting its own pressure, which we call the partial pressure. And in sum, each individual species is adding up to exert the total pressure that this mixture of gases is exerting on the volume. Okay, so let me write that down because that's really the critical concept here. Okay, so each species in a mixture of gases exerts its own individual pressure on the volume containing the gas. We call this exerted individual pressure the partial pressure of the gas. Thus, each individual gas's partial pressure adds up to exert the total pressure of the mixture of gases on the volume. Okay? So each individual gas has a partial pressure. So there's a P circle, a P triangle, and a P dot. Okay? So these are the partial pressures of each individual gas. In the mixture. And then there is what is called a total pressure, which is the sum of each of the individual partial pressures. P circle plus P triangle plus P dot. Okay? Okay, so we can basically show that P total, to write it more mathematically or scientifically, if you will, P total is the sum from I equals 1 to n number of species, the partial pressure of each individual species, Pi. Okay? So this notation that I've written for you here is basically the same as saying P1 plus P2 plus P3 plus ... plus P sub n, where P1 is the partial pressure of gas 1, P2 is the partial pressure of gas 2, P3 is the partial pressure of gas 3, all the way up to Pn, which is the partial pressure of gas n. Okay? Now, for an ideal gas, and this is only for an ideal gas, we can likewise say, since n of an ideal gas equals PV over RT, that n total, the total number of moles in that mixture of ideal gases, is equal to the sum from I equals 1 to n number of species, n sub I, or n1 plus n2 plus n3 plus ... plus n sub n. Okay? In other words, the total number of moles in this ideal gas mixture is the number of moles of species 1 plus the number of moles of species 2 plus the number of moles of species 3, all the way up to n number of moles of the species, or up to the nth species number of moles is the correct way to say that. Okay, now, you might look at this and you might say, well, okay, first of all, why did he make such a big deal about saying that this is only for ideal gases? You know, what other type of gas is there? Well, there is something which we call a real gas, and we're going to discuss real gases in part 3, hopefully part 3 if I can get to it, of your lecture, chapter 5, might be part 4. It's the last section of chapter 5. So there is such a thing as real gases. And so then you might say, well, okay, if that's the case, then how can you say that for a real gas, this statement is not true, right? Where n total is equal to the sum from I equals 1 to n of n sub I, it seems like even for a real gas, the number of particles of a real gas should be the same as the number of particles of an ideal gas. Well, that's a reasonable question to ask, and what it requires me to do is to remind you that this idea of a mole, the concept of a mole, is rather abstract, okay? Remember that we don't actually count the number of moles in a physical system, okay? We can measure the mass, we can measure the pressure, we can measure the temperature, but we can't measure the number of moles. It's an abstract concept. It's a theoretical construction that allows us to come up with these relationships, okay? We can, in fact, say that the total pressure of a system is P1 plus P2 plus P3 plus ... all the way up to Pn, because we can measure the individual pressures of all of those components, but we can't necessarily say the same thing for the number of moles, okay? Now, as I say that, when we get to actually discussing real gas behavior, it's actually pressure that we're going to make a correction to. We're going to make that correction based on the number of moles in the system. But again, that's all because we can only measure the pressure of a system. We can't actually measure the number of moles, okay? More on that later. In the meantime, part 2 is finished, and I wish you a great rest of the day. We'll continue finishing chapter 5 in part 3